Okay, very good. And yeah, we sally forth. So yeah, so last time, to recall a little bit what we did, so we constructed some modular categories, and particularly we constructed some, some pointed ribbon fusion categories, and then we said that sometimes they're modular. So in fact, there's a classification of pointed ribbon fusion categories and of the ones that are modular. So, pointed ribbon fusion categories are classified, and it's also true for modular tensor categories. And well, we kind of know roughly what to do. So a pointed fusion category corresponds to G-graded vector spaces with some 3 cocycle. So it's just a question of, well, how do you put a ribbon structure, a braiding and a twist, a ribbon structure on that, and when is it modular? And so one can sort of just go through this, and you find the answer. And actually, there's a very beautiful characterization of these in EG&O. There's a theorem that says that pointed ribbon fusion categories correspond to pairs GQ, and here Q is a quadratic form. On G, and of course G should be an abelian group, finite abelian group. Okay, so it's a quadratic form on this. Okay, and so that's sort of part 1, and part 2 is that if we put in modular into categories, corresponds to the same, but Q should be non-degenerate in a specific sense. And in what specific sense is it? So Q should be non-degenerate in the sense that if we form the bilinear form BGH is equal to Q of G, Q of H divided by Q of GH, then this form is non-degenerate in the sense I mentioned last time. And I should say it's a quadratic form, so it goes from G to non-zero numbers, so it's that kind of quadratic form. I'm thinking of G as being multiplicative here, et cetera. Okay, so that's all of them. That's the pointed ones. These here are often called pre-metric groups, and these are called metric groups if it's non-degenerate, and so that gives a complete answer. Right, so these are nice, but of course, as Victor mentioned in his last talk, we would like to have more interesting examples. And he introduced some of these. So more interesting would be these categories that I will call CGL. He put the letter K here, and it's a different number, but they're related by a linear function, so there's a way to work it out. So what do I mean? So here I start with G, should be a simple Lie algebra. And then I look at this quantum group, UQG. And, well, as Victor said, you have to be a bit careful. But so what I'm going to do is I'm going to have Q be e to the pi I over ML, to be very explicit, where M is 1 if G is of type AD or E, M is 2 for type B, C, and F4, and M is 3 for G2, type G2. Right? So that's the root of unity I want, and so that's where the L comes from. And, well, you have to do a number of things. First of all, you can't just take the quantum group you started with. First of all, notice this is the big quantum group, not the small one. So big quantum group. And one actually has to consider a subalgebra generated by something called the divided powers. So there's a smaller thing. And then you look at the representation theory of that at a root of unity. It's a very disappointing kind of theory. It's not semi-simple. And whereas we usually, in Lie theory, if you have a dominant weight, there is a unique irreducible associated with it. That's not true anymore. There's lots of issues. But fortunately, there's a subcategory of the tilting modules, which are modules over this Hopf algebra that are particularly nice. So they have filtrations. And what kind of filtrations? Well, they're called good filtrations. Okay? So we know they must be good. Anyway, so this forms a nice category, which you can then take a quotient by a tensor ideal of negligible morphisms. Right? And so anyway, these are all words one can Google. I'm not going to explain. But one does get a category out of this, and it's these ones. Okay? And so these are what I will call sort of quantum group categories coming from these. Now, Victor said, well, these are fusion categories, and they certainly are, but they're even better. They are typically modular categories. Okay? And I've been very careful to put this M in, which will actually indeed guarantee that these are modular. If you're not careful about that M, you might get something that's only ribbon. There's issues. But, okay, so these are the categories we're interested in. So let me give you, yes, question. Sorry.
Are these the same as, do these describe rational homology theories?
Yes. Yes. Question.
Can you not start with a small quantum group, or does it just, maybe you can, but you don't do that?
So the representation theory of the small quantum group is not semi-simple. It already has finitely many simples. I honestly don't know what happens, but my understanding is that if you start with a small quantum group, you won't get these. By
you can still somehow simplify, but you maybe get some other things.
yeah, maybe you kill everything. I don't know. They're definitely different. There's other experts in the room that. So yeah, I agree that it's in his book, but he uses Anderson-Paradowski, which uses the large quantum group. I'm not sure. I've read that section, but yeah, it's in a book. But yeah, we'll see. Yeah. Turaev's book on three manifolds. Yeah. Anyway, I don't. But maybe what I should say is I don't understand his construction. Yeah. Okay. So anyway, so we get these. So let me give some very explicit examples of this, so that we can kind of see what they look like. So. Let's start with, let's take G to be SO5. Yeah, so type B2. It's a good one, right? So rank 2 Lie algebra. And let me take L to be 5. In other words, Q is E to the pi I over 10. Okay? And let's see what happens. Well, first of all, let's draw the dominant Weil chamber of type B2. This is what it looks like. It's here. It's this stuff in this cone here. And so let me start writing down the dominant weights, so the things that sort of can show up. So, of course, you have trivial. You have this one, which is usually, so that for SO5, this would be the 5-dimensional representation. So I call it V, the standard representation. This guy here is the adjoint representation of the category. But you have spin as well. So I'll put in spin-looking things by an X. And so we have more. And so it just sort of continues in this way, like this. Sorry, X there, et cetera. So you just sort of continue. So if you want actual coordinates, that's 1/2, 1/2. And this is 1, 0. And everything else is a sum of these. Okay? All right, so that's if I was giving a course on Lie theory, right, that's what this is. This is the representation theory. Well, what happens when L is equal to 5 is at some point the corresponding tilting modules start having quantum dimension 0. And this is sort of bad. Yeah? So we want to kill that. The first place in this case where you get quantum dimension 0 is along this hyperplane. So you draw sort of a wall through there. Maybe it should be another color if I was cool. Okay. So we have this color. Yeah. So there's this wall. So you've already got these two walls, but now notice it confines everything. So there's finitely many simple objects. In this case, 6 of them. Okay. That's what remains after this quotient. And while you can describe fusion rules, et cetera, maybe the thing I will give, the information I'll give you just, you can work these things out, is the dimensions. So the dimension here, that's 2-dimensional. These two are square root of 5-dimensional. This is also 2-dimensional, and that's 1-dimensional. Okay. So anyway, you get lots of information. You can work out the fusion rules, the tensor product rules. Basically, you use the tensor product rules for SO5, but if you get caught crossing this border, then you have to reflect back in, okay, with a negative sign. There's various rules, okay? But one can describe these completely, okay? So maybe a few years down the line when our collective sense of humor is recovered, we can make jokes about walls like this, but for now, I'll leave it. Okay, so yeah, so this is the SO5, what I would call SO5 level 2, has rank 6. So this is often also denoted by SO5 level 2. So when Victor was talking about he had a K, that's this number here. K is the level in this case. Okay, so that's an example. This is actually turns out to be a metaplectic category, which is kind of fun. Okay, so that's an example. Let me give a couple more standard ones. So if I look at SL2, that's sort of 4th roots of unity. What is this? Well, now, right, this is just on a line, right? That's the, the dominant. This is already the dominant Weil chamber for type A1. And so you have the trivial representation, and in this case, we have something like this. Maybe one more. Yeah, just like that. Okay. And so let me. So this will have 4 simple objects. So there's a wall here. Okay. And the dimensions are 1. These are both tau, where tau is the golden ratio. Okay. That's this theory. And it turns out that this has a subcategory. If I choose this object, it's tensor square. So let me call this thing maybe A again, because it's like an adjoint representation in some sense. If I take A tensor square, I get the trivial plus A back again. That's it. Okay. And notice here, this is 1-dimensional, which means I have a pointed subcategory generated by it. Anyway, I can call this something. I'm going to call it S. S squared is 1. So actually, inside this category, I have 2 subcategories. Okay. Turns out they're both modular. This one is known as the Fibonacci theory. This one is the semyon theory, corresponding to Z2. So this actually breaks up into semyon. I may be wrong. It might be semyon conjugate, but I'm not going to worry about that. And then this is Fibonacci, something like that. Okay. So these are famous categories already. Let me give you yet another one which shows up very often in the literature. Sorry, I've made a mistake here. This is a 5. It's at 5th roots of unity, obviously. It's not going to work. Okay. The one I want to do now is this. So if I take C SL2 4, this corresponds to something called the easing theory. And what does it look like? Well, it has three simple objects: trivial, sigma particle, phi particle. This is usually, so if you ever hear people talking about the Majorana fermion, there it is. Okay, that's it. So what does this look like? Well, the dimension of the sigma particle is square root of 2. The dimension of the phi particle is 1. The twists of the sigma particle is e to, in this case, 3 pi over 8. So it's, I'd say it's an easing. There are 8 of them. And this guy here has twist minus 1, which makes it a fermion in our nomenclature. Okay? And I can, maybe I'll even give you the S matrix. What does it look like? So I mentioned last time you can construct a matrix for every, sort of with labels, pairs of simple objects. So this looks like this. Like that. Okay. So that's its S matrix. Its determinant is non-zero. And there we have it. And okay, so this is 3 examples, very explicit examples of modular categories coming from quantum groups. Okay, any questions?
So is there a statistical mechanical connection?
Potentially, but I don't know it. Yeah. Yeah, at some point I'll ask someone, maybe Fiona, why the word easing is used for this. And so now she's warned, she can go. Say again?
What did you call sigma again?
Yeah, so I would call that the sigma particle. Maybe the Majorana particle is sometimes what it's called. It's not the fermion, it's the other one. Yeah. Did you hear me say something unpleasant about it? No. Okay. I like that particle. That's a good one. It's a non-abelian anion. It's the first one that one will discover if they exist in nature. Okay, good. So that's this. So let me make a remark. So what I've written down is stuff called modular data. So there's a talk devoted to this by Colleen Delaney this week. So you'll hear more about this and how to think about them. But one of the things that's related is one rather interesting thing is if we're going to define T in general, a matrix T, to be a matrix whose ijth entry is, well, it's a diagonal matrix, and its ijth entry is the twist on the ith simple object. Okay? So it's a diagonal matrix. And, well, we already have S, which is, you can think of it as sort of this picture here. It's the invariant associated with the Hopf link with the 2 strands colored by simple object I and simple object J, let's say. Okay. So this is a perfectly good matrix. This is Sij. And what are they good for? Well, they're good for lots of things, but one thing in particular is that S and T give us representations of SL to Z, the modular group. And so this is why we use the word modular. It's because we get this. This is the modular group, and we get a representation of it. How does it work? Well, SL2Z it can be generated by 2 matrices I'll call S and T. And here S is the matrix 0, -1, 1, 0. And T is this matrix here. Okay. And I should add a little word here because I haven't bothered to scale or anything. These are only projective representations of this thing a priori. Particularly, this matrix doesn't have determinant 1. So that would be a problem, and neither does T a priori. But anyway, you get a projective representation of this thing, of course, by sending S to S and T to T. Okay, so, yeah, so that's the reason for the nomenclature. Okay, so that's this this fact here. Maybe it's a good time for a theorem. So let me mention a theorem. So this is a theorem due to Ng and Schauenberg. So SL2Z is obviously a big group, yeah, infinite group. Here we've got a representation of it. We can look at its image. It turns out that the image of, so let me give this representation a name, maybe capital Phi. The image of Phi is finite. So take any modular category. You've got an S and a T matrix. You can construct a representation of projective representation of SL2Z. Its image is finite, and in fact factors over. And I'm being a bit sloppy here with projective versus not, but it factors over SL2Z mod NZ, where N is the order of the T matrix. So obviously, this representation would not have finite image if T had infinite order. T must have finite order. This T obviously has infinite order, yeah. But this T here, this diagonal T, has finite order. Turns out that all of these theta i's are roots of unity. Okay, and so that's sort of what makes this at least possible. Okay, good. So we have this representation. And I've explained the word modular at least. Okay. So let's maybe think about the question that Victor asked about classification. What can we say about classification for modular categories, right? For fusion categories, it's hopeless. For modular categories, maybe there is hope, right? There's extra adjectives, and that helps. So that's kind of a question. So how many modular tensor categories of rank R, for fixed R? Okay. So for fusion, it is known, so if you restate this, it's known that it's finitely many for rank 1, 2, and 3 if you add the adjective pivotal. For rank 4, it's unknown whether this is finite or not. So anyway, this is kind of the question. But let me first talk about this kind of in practice. So suppose we fix some rank R, and we would like to try to classify all modular categories of that rank. What can we do? Well, so let me first kind of try to answer this question sort of in practice, and then give you some theory, more theory. So it turns out that all of this information can be used, so the modular data, for example. So sort of the first step one does is you can define a field, say K0, which will be, I'm going to take Q adjoint, so it's a Galois field, the entries of the S matrix. Okay? So you've got an example here, right? So in this case, that field is Q adjoint square root of 2. Right? It's a nice finite dimensional extension. It turns out, by another theorem of Ng and Schauenberg, that this is a subfield of Q adjoin the thetas. Okay? The thetas are roots of unity. So a priori looking at this, you might be worried about, Galois theory, and when you get like degree 5 polynomials, things could get bad, right? But this is a cyclotomic extension. And so the Galois group from Q up to here is definitely an abelian group. So that's good, right? That helps a lot. Okay. So that's sort of the first step. So you can use the fact that Q adjoin theta I over Q the Galois group here is abelian. So that gives us a little hope. Okay? So what are we going to do? Well, we're going to try to use some Galois theory to understand, to try to figure out what's going on with these things. Okay? So that's kind of one step. And by the way, this, of course, is Q adjoin maybe zeta sub n, where n is that same n, the order of the T matrix. Okay? So that's abelian. So that's one fact. So A. Another useful fact is that if you look at the Galois group of this K0 over Q, it's a subgroup of SR. That R. Okay? So not only is it an abelian group, it's an abelian subgroup of this symmetric group. Okay? So now we're really limiting things down. Okay? So, and one more thing that one can check. So there's another Galois group that we should consider. We've considered the top two, or the top and the bottom. What about the Galois group of Q adjoin this zeta n over Q over K0? It's also an abelian group, but it's even better than an abelian group. It's an elementary 2 group for some K. So the Galois theory of modular categories is really quite beautiful, and it's not so bad. Yeah? So that sort of gives us some hope. So, right, so then what do you do? Shift these. Okay, so the kind of what we're playing with here is maybe we fix an R, maybe a rank, maybe rank 2 or something like that. First case where it's something to think about. If R is 2, then we're looking at abelian subgroups of Z2. There's not a lot going on, right? So at least the Galois theory is pretty well in hand. So now what do you do? Well, so step 2 is, well, you fix an abelian subgroup of, say, SR, and we bifurcate. Okay, so we just consider each Galois group one at a time. If R is small enough, there aren't that many, right? They're abelian, and, well, if R is small, there's really not so many going on, okay? And so then so this is sort of where the magic has to happen, really black magic in this case. So what do? So you fix this thing, and then you use everything you know to determine the matrix S. Okay? So a priori, S is just some arbitrary matrix with some algebraic integer entries, as it turns out. And, well, you do something. So one of the things that you can do is, well, you just use Galois theory, play around with it, and this gives you some relationships among the entries of the S matrix. But you can also use this fact here, that the image of this thing is finite and it factors over some group that potentially you have some handle on. And so you can study the representation theory of these groups, or finite groups, and to try to understand what goes on. So anyway, so this is sort of the hard part. Yes, question? Yeah?
Do you know anything about in terms of how ones you are being acted on in terms of orbits?
The orbits of the Galois group? Yeah, so, right. So, it turns out that the Galois group actually acts on the columns of the S matrix. Once you normalize them, it actually permutes them. That's how you get this SR here. So you know quite a lot, in fact. So let's say you have the R cycle, 0 through whatever, R minus 1. Then that gives you a lot of information about relationships among the entries of the S matrix. There's quite a lot. So yeah, we know. So it isn't necessarily transitive. yeah, so you could have some columns that are sort of fixed by it, others that are not. That's quite possible. But you can use all that. That's exactly what's going in here. So it's extremely important to know this. But it's case by case. Yeah. So, right, so anyway, so you try to determine S. And then what do you do next? Well, it turns out that there's something called the Verlinde formula. It determines the fusion rules from S. So this S matrix, it looks sort of innocuous, right? It's just something, right, you got by tracing out some hop links. But in fact, you can determine the fusion rules from that, okay? And now we're all in business because my version of corollary to Oaknian rigidity is that there are finitely many modular tensor categories with some fixed fusion rules. Okay, so Oaknian rigidity actually says that if you fix the fusion rules, then there are finitely many, at most finitely many, well, I guess 0 is a finite number, finitely many fusion categories with those fusion rules. And then you can say, well, how many braidings can there be? Again, it turns out to be finite. How many spherical structures can there be? Again, it's a finite thing. So you've made a lot of progress, at least here. Okay. So that's really how we tried to classify low-rank modular categories. And it's been successful up to rank 5 with lots of progress on rank 6. Okay? But this also looks slightly dissatisfying for the following reason. All you know are, okay, here's some fusion rules, right? You've got, say, finitely many. Let's suppose this works. What do you do from there? How do you actually classify these categories up to equivalence? Question?
So you're saying that for every abelian subgroup of SR, you can construct an S matrix?
I'm not. I'm saying that for many of those abelian subgroups, it's impossible to have an S matrix. But you can eliminate things. That's typically, in fact, what happens. Yeah. Okay, other questions? So this is kind of the basic process. Okay, so another direction. So suppose you fix the fusion rules. You might say, okay, how do we actually classify all of the modular categories with these fusion rules, right? And so that's sort of a more general question that is essentially open. So if we fix fusion rules, or maybe the actual fusion category, it's still an interesting question, right? How do we classify all modular categories, right? So classify sort of modular structures on these, with these fusion rules, okay? So, of course, Oaknian rigidity says, as far as going from fusion rules to a fusion category, there's finitely many. But it's not constructive, right? It's sort of one of these arguments, well, you can't deform. So that's the question already, to go from here to here. Quite interesting question. There are some special cases that you can use where a particular set of fusion rules, it's possible to classify all fusion structures on that. For example, there's so use things like, there's a paper by Kajda and Wenzel that deals with the ones associated with SLN at some root of unity. But only it sort of determines fusion categories from fusion rules. And so you might ask, well, when can you put braidings on these? And this is an interesting question. So that's one question. Turns out there's another recent result that for fixed fusion rules, Dmitry Nikšić has a way of trying to understand understand the bratings on a fixed fusion category that admits a brating, let's say. So for example, you have some category, you've got one modular category with these fusion rules. Can you understand all of them, all the bratings? And that's true. And then there's one more step, which is the spherical structure. And that's actually the easiest one. So spherical structures, SP, on an MTC, and I'm cheating here, so what of course I really mean is take an MTC, forget the spherical structure, and see what other ones you can put on, but it should be modular to start with, are in one-to-one correspondence with order 2 invertible objects. Well, order less than or equal to 2 invertible objects. Okay? So it's quite possible you don't have any of order 2, but you always have one of order 1, namely the trivial object. That's an invertible object of order 1. It gives you a spherical structure, and so this does the job. Okay? So we really can make some progress in this direction. But this is still quite a general question. So somebody throws some fusion rules at you and says, okay, I know this has a modular structure above it. Find me all of them. Roughly, you need to follow something along these lines. Okay? And of course, this is rather specific. Okay? So that's an issue. Okay, so, well, why is this even conceivable? Well, of course, we didn't care if it was conceivable. We went ahead and started. But it turns out that there is a theorem that answers this question more generally. So, sort of general answer to, I don't know, question 1 is a theorem. So this is Brouillard, Ng, myself, and Shenghang Wang. And it says the following. There are finitely many modular categories of any fixed rank R. Okay. So this is called rank finiteness theorem. Okay. So anyway, so this is the theorem. I won't go into the details of the proof of this, but I'll just sort of say it uses some various results. One of them is something called the Cauchy theorem. So it's sort of the analog of the Cauchy theorem for groups, for actually spherical categories. And it says something about the dimension of the category. It relates the dimension of the category and this number n. It turns out if you take the norm, number theoretic norm, of the dimension of the category, the primes that show up in the factorization are exactly the same as the primes that show up in the factorization of n. So that's sort of Cauchy theorem. And then from there, you use various results. One interesting thing is that this n here, there is a bound on n in terms of r. So that's good. So that bounds some things. And then there's one really amazing result from analytic number theory due to Averza from 1984 that describes solutions to something called S-unit equations. And that's sort of the final step that really does the job. But anyway, this is known now. And then, yeah, of course, eventually use Okiniano rigidity again. So any questions? Okay. So let me move on to another kind of question that's interesting. It's kind of related to this theorem of Ing and Schaumburg. So, let's see be, for the moment, just a braided fusion category. And let's let X be an object in C. Well, what can we do? It turns out that we can get an action. So this is some fixed thing. So I can get, first of all, I'm going to describe a map C from Bn to the group of automorphisms of X tensor N. Okay? So, of course, if I take X tensor N, I can look at its endomorphism algebra. Okay? So I can compose. So these are morphisms from X tensor N to itself. I can compose them. That's a perfectly nice algebra, actually a semi-simple algebra, Artinian, finite dimensional, everything's nice about it. And then we can look at, well, the invertibles in here. Since I want this to be a group homomorphism, that's what I do. And how does this work? Well, you use the braiding. What else, right? So you apply this to the generators of the braid group, sigma I. Right, these are so the generators look like this. That's sigma I. It's where the I and the I plus first one get crossed. And I take the identity on X, tensored with itself I minus 1 times, tensored with the braiding of X with X, and fill it out. So N minus I minus 1 times. So this gives me a group homomorphism. Okay? And now I can consider the modules of this thing to get modules for the braid group. So how do I do that? Well, that group, the automorphisms of X tensor N, has a nice faithful representation we can use. Namely, so aught X on what? Well, I'll call it H sub N upper X. And it's defined to be the direct sum over irreducibles, simple objects in the category. And here I'll take hom Y to X tensor N. How does it act? Well, by composition, in the obvious way, on each factor. Okay? So we get a representation, depends on X, the simple object, from Bn to GL of this big old thing. This GL will factor over this direct sum, so you can really write this as a product. Each one of these may or may not be irreducible as a braid group representation, but they're certainly, each of these modules is simple for the automorphism group there. So this is the representation we get. Okay? So that's one of the main uses of braiding. We get this representation. And of course, in the topological model for quantum computation, this is how you get quantum gates. So it's quite important in applications as well. At least some of the quantum gates. Okay. Good. Okay, so here's a question we can ask. Right, what is the image? Potentially inspired by this question here, which originally was a question of Gannon, and Ing Schaumburg answered it in the affirmative. But, right, so this, right, why should it be finite? Well, over here you can ask the same thing. When is it finite? And certainly it's not always finite. It's not always infinite, so you might wonder. Okay? So maybe a slightly better question, also related to universality of the topological model for quantum computation. When is it finite? And of course, if you know when it's finite, you know the rest of the time it's infinite, so that's also good. Okay. So let's say X has property f if the image for all n is finite. Okay? Property f. Okay? So, well, we might consider this question. So I've given you two examples of modular categories. No longer here, but they're somewhere. And so we can let's just ask that question for here. So fib, so you take the non-trivial particle in fib. So fib does not have property f. On the other hand, any easing does. Okay, so two examples. Any pointed category has property f. In fact, the Bragg group image is more than just finite. It's abelian if you take a simple object. So it's not so very interesting. Okay. So, well, one of the ways in which it seems to be related involves the following piece of information. So I'm going to give a definition. So let's take X, for the moment, just a fusion category, all that matters. Okay. Well, I can look at n sub X. This is the matrix of fusion with X on, the simple objects in this category. Okay, there's finitely many. In other words, n sub X ij will be equal to the dimension of Hom X tensor, say xj to xi, something like that. Okay, so these numbers. So we've got a nice matrix. Okay. And I'm going to define fp dim of x to be the largest eigenvalue of this matrix of fusion with x, the largest element of its spectrum. Okay. So that's the Frobenius Perron dimension of x. Okay. So for x simple, we can say x is weakly integral if I take this fp dimension of x, square it, and get an integer. Okay. Okay, so that's a definition of weakly integral. More generally, a category is called weakly integral if all of its simple objects are weakly integral. So that's the general idea. Okay, so so now I can state a conjecture. So we say x has property f if this is true. We say x is weakly integral if this is true. And so you put these together and make a conjecture that says x is weakly integral if and only if x has property f. Okay? So that's the conjecture. And, well, there seems to be mounting evidence that it's true, since it's still called a conjecture and not a broken dream, I guess is the other. Okay? So this conjecture is true in a bunch of cases. Obviously for pointed, right? This is like exercise. Any simple object in a pointed category has dimension 1. That's certainly an integer when you square it. 2, it's true for group theoretical braided fusion categories. And so this was Eddinghoff, myself, and Witherspoon proved this. So you haven't got a real definition maybe of group theoretical, but it was mentioned in Richard's talk. I can give you an example. If you look at rep D, so the Drenfeld double of a finite group, possibly twisted, this is group theoretical. Okay, so that's it's true there. The conjecture, so these are integral, and so the content here is proving that the braid group image is finite. But what about if we look at quantum groups? Sometimes they are weakly integral, sometimes not. Fibonacci is not weakly integral. If I square the golden mean, I don't get an integer, but easing is. Similarly, this metaplectic SO5 level 2, that is weakly integral. So you can ask this. So this is true. So it's known for all quantum groups. So this goes back to lots of people have been verifying cases of this. So the first one, I think, was in Jones's paper from the Kyoto conference in '83 or something. So Jones and then Friedman, Larson, and Wang verified infinite image for a bunch of cases. And then myself and Wenzel did some cases. I also did some cases with Larson and Wang. Anyway, these are names associated with this, but it's now complete, and that's the story. But there's one more case that has recently been proved. So last year, Green and Nikšić proved it for so-called weakly group theoretical braided fusion categories. So it's now true for this as well. Now, I don't want to say what weakly group theoretical are. There's various ways of describing these. But the nice fact, well, there's another conjecture that might make it so that you don't have to know the definition. And that is, there's a conjecture that says that weakly integral and weakly group theoretical are the same thing. It is true that every weakly group theoretical braided fusion category is weakly integral. The converse is not known yet. But if we knew that, then one direction of this conjecture would be completely handled. The hard direction, in my opinion, showing finite image for weakly integral. Okay. So, right. So this is these are a couple of results that have been obtained in the theory of modular categories recently. But I should maybe in the last moment I'll just tell you there's lots of other interesting areas to study. So interesting questions abound in this area. One of them has to do with the Witt group of non-degenerate braided fusion categories. So you can take all non-degenerate braided fusion categories, take equivalence classes, Witt equivalence classes, and turn it into an abelian group. And this is a really amazing group that one can study. There's lots of really cool properties, which might help us understand at some high level the classification of non-degenerate braided fusion categories. I'll stop there. Thanks. Very top, yes? Non-trivial in the sense of non-abelian? Yes. So quite a few. Most of them are constructed from SL2 at some small level or a subcategory of those. So you've got Fibonacci, et cetera. So really most of them. Now, there are a few that have finite braid group image, but non-abelian. So if you look at, for example, SL2 at sixth roots of unity, this happens. So there's quite an interesting landscape of these. Yeah. Dave?
This property F, so you gave us a list of some constructions of one modulus which you categorized from another one, and also Victor gave us some like G extensions.
Yeah.
So do you have any work about which of those operations preserve property F?
So yeah, that's certainly reasonable. So there's a number of results. For example, I guess Drinfeld center would preserve property F. Yeah, so if you have property F and you take the Drinfeld center, it'll again have property F, and vice versa, if you right, for an obvious reason. I guess that's true. So you might wonder about, so this result here makes one suspect that probably gauging and boson condensation should be okay. There's maybe potentially a question about that. It just depends on whether, the answer to that other conjecture, I guess, would be part of it. At least one direction's okay. Right, so, and of course, Deligne product, that's fine. So lots of things are fine. We have a new method called zesting, and that turns out to preserve property F and non-property F, for that matter. Yeah, but it's certainly a very good question to study. That's a good way to go about it. Yeah. Sure.
Why, if you want to study the property F, why restrict to non-degenerate categories? It seems like if you are degenerate, you're just more likely to be.
Yeah, so, right. The conjectures for braided, but they're basically equivalent, because if you have any braided fusion category, you can embed it in its double and it'll be modular. So you don't lose anything. But you're right, you should study it from this perspective. Yeah, question up there?
The SO5-2 category,
Yes?
is it possible to construct it from the Fibonacci category? I just asked because there's a square root of 5.
So it depends on what tools you allow me. None of the tools that I would regard as sort of being legal would do it. So I would think of like gauging or these kinds of things. That actually preserves weak integrality, and so no. But I know there are some physics papers out there that say something like maybe there's some way of playing some game with these, but it goes beyond sort of what I would consider as being constructions that are well understood at this point.